Good evening, student. So today we'll continue our discussion on constraint optimization. So in the last class, we discussed about the necessary and sufficient conditions for optimality for constraint optimization problem having equality constraint. So today we'll discuss about inequality constraint, and then basically we'll try to find out the necessary condition for optimality. So as you know, a multivariable problem with inequality constraint can be written like that. So here we are considering a minimization problem, and the minimization of fx. So it's a n variable problem. So we have x1, x2 up to xn, and subject to the constraint the zjx is less than 0. So we are only considering the inequality constraint here, so we'll not consider the equality constraint. Okay, and there are m constraint here, so j is varying from 1 to m. So j is varying from 1 to m. Okay, so it's a minimization problem, minimization of fx subject to zjx is less than 0. So now the constraint, the zjx, I can write it, or I can add this yj square just to make it equal. Okay, so I'm putting this variable here yj, and just to make it a equality constraint, and then basically I can apply the Lagrange multiplier method. So I have put this yj square, so this is just to make it equality constraint. So I'm just writing this zjx which is less than equality type constraint, and I'm writing zjx plus y square which is equal to 0. Now the problem is something like that. So if we convert it to an equality constraint, the problem will be something like this. So it's a minimization of fx subject to capital zjxy. Now y is also variable because because you are making it equality constraint by putting y. So now it is a function of x and y, and which is equal to zjx plus y square equal to 0, and where y equal to y1 y3 so up to ym. So we have actually m constraint here, so there are total it's up to y1 to ym. Okay, so I hope this is clear to you. So the concept is very simple, or I think clear itself. So what we are doing here, we have converted the inequality constraint to equality constraint by putting y square here. Okay, so that I can apply the necessary condition for optimality in the Lagrange function. Okay. So this is the problem. Now minimization of fx subject to capital zxy. So zxy is zjx plus y square 0, and j equal to 1 to up to m. Okay, now I can write the Lagrange function like this. So Lagrange function is, now it's a function of L is a function of x, y, and lambda. So this is fx plus summation of j equal to 1 to m. So we have total m constraint. So lambda j capital zjxy. So this is the Lagrange function. I hope this is clear to you. Already we have discussed in the last class about this Lagrange function, and then I can apply the necessary conditions for optimality. Okay, so on this Lagrange function, so I can write this necessary condition something like that. So the necessary condition is the derivative with respect to the variable, partial derivative with respect to the variable should be equal to 0. Okay, so if you take the derivative with respect to xi, so then I am getting del L by del xi, which is equal to del F by del xi, then summation of j equal to 1 to m lambda j del g by del xi. Okay, so I'm getting this the with respect to xi. Similarly, I can take the derivative with respect to lambda z. So if you are taking with respect to lambda z, then you are getting zxy equal to 0. That means small zx plus y square equal to 0 if you are taking with respect to lambda, and if you are taking with respect to y, then you are getting twice lambda z yz equal to 0. Okay, so these are basically the necessary conditions we are getting. Just we have applied the necessary condition for optimality, and finally we are getting optimality on the Lagrange function, and we are getting all these equations. Okay, now yeah, so from the last equation, okay, so last equation is that the derivative with respect to y, okay, del L by del y. Okay, so if you do that, so you are getting twice yz lambda z, or twice lambda j yj is equal to 0. So we may get two conditions here. So either yj that lambda j equal to 0, because this is a multiplier, this lambda j and yj are it's a multiplication term. So either yj equal to 0 or lambda j equal to 0. So lambda j equal to 0, there may be two conditions only, that if lambda j is equal to 0, then the terms will be equal to 0, or yj equal to 0, then the terms will be 0. So there are two conditions, either lambda j equal to 0 or yj equal to 0. Now what will happen if lambda j equal to 0? Okay, so if lambda j equal to 0, the constraint is not active, hence can be ignored. That means yj is basically yj, if lambda j is 0, that means yj is not 0, suppose. Okay, so in that case what will happen, if yj is not 0, that means that that constraint is not active. That means the basically whatever solution you are getting, that will not be on that particular constraint. So I can say that if lambda j equal to 0, the constraint is not active, hence we can ignore that one, because the solution whatever we are getting, that is not influenced by that particular constraint. So therefore I can ignore that one. Similarly, if yj is 0, means yj is 0, that means zj equal to 0. Okay, so that is the equality constraint. If yj equal to 0, then the constraint is active. That means that solution is on that particular constraint. Okay, so therefore hence we have to consider that one. So therefore I'm getting two types of your equation. So one is that lambda j equal to 0, or one is that yj equal to 0. Now let us consider all active constraints. So what is active constraint? Active constraint is that lambda that basically that yj equal to 0. Yj equal to 0, that means lambda is not 0, yj equal to 0. So yj equal to 0 means that constraints are active constraint. Okay, the solution is on those constraints. So let us say that J1 is the set of active constraints. So I'm considering two sets. So we have total m constraints. So out of m constraints, suppose some constraints are active, some constraints are not active. Okay, so I'm taking two sets. The first set is J1, the active constraint, set of active constraint, and second set is J2, that is inactive constraint. So inactive constraints you may not consider. Okay, so if I know that these constraints are not active, so I will not consider those things, but if I know that these constraints are active, then I have to consider that constraint. So the optimality criteria now can be written for the active constraint. Okay, so means the optimality condition can be written now, that is that derivative with respect to x, with respect to xi, then lambda j, then derivative of zj, del derivative of zj is equal to 0. Okay, and then this is the set of active constraints. So therefore this active constraint means that yj is 0, so therefore zj zx equal to 0. So this is the active constraint. And for inactive constraint, so you have to consider that zx plus y square equal to 0. So I'm just putting two sets now, the one set having active constraint and one set having inactive constraint. So inactive constraints are, that is your set your Z2. So now if I take the first condition, basically, so if I take the first one, then if you look at, so I can write I can write this equation, this particular equation, yeah, so I can write it like this, that negative of del f by del xi, which is equal to lambda 1 plus del g by del xi plus lambda 2 del g by del g2 by del xi up to lambda p, or basically lambda n, basically. So maybe it can go up to lambda n. Okay, so it can go up to lambda n. So I'm getting I can write it something like this. Okay, so I can write it. So this is minus del f is equal to lambda 1 del g1 plus lambda 2 del g2 plus lambda 3 del g3, yeah, so up to lambda m. So we have total up to m constraint. Okay, so up to m, okay, so this is up to m constraint. Okay, del gm. Okay, so I can write it like this. So where, yeah, so where del f equal to this and del g equal to, I can del z equal to, I can write it like this. Okay, so now let us consider. So this indicates so what is this equation is telling? This equation is telling that the negative of the gradient of the objective function, so this is the negative of the gradient of the objective function, can be expressed as a linear combination of the gradients of the active constraint. So gradient of the active constraint, so I can write it like that. So gradient of the active constraint at optimal point, basically. So you just see at optimal point what will happen. The negative of the gradient of the objective function is basically the linear combination of the gradient of the active constraint. So we are only considering the active constraint here, basically. Okay, so I can write it that minus del f, which is equal to lambda 1. Suppose if I take only two constraints. Okay, so just to explain the concept, so I am considering two constraints, and these two constraints are active constraints. So that is minus del f equal to lambda 1 del z1 plus lambda 2 del z2. So these are two active constraints. And now if I take a feasible direction, so I will explain with a diagram in the next slide. So let us take, suppose this is the this is the condition at optimality, so that negative of the gradient of the objective function is a linear combination of the gradient of the constraint function and active constraint function. So what I am doing here, I have considered your two constraints, just to explain the concept, two constraints, that is z1 and z2. So in that case I can write that del f, okay, so negative of del f, which is equal to lambda 1 del g1 plus lambda 2 del g2. Okay, now you consider, so you are at a particular point now, okay, and you have basically, there is a feasible direction. Okay, so in that, suppose s is a feasible direction, so in that case what I can do, I can multiply it, this equation by s. So in that case I am getting that negative of this s del f, which is equal to lambda 1 s your del g1 plus lambda 2 st del g2. So I can write it like this. Since S is a feasible direction means that you are going towards, you are going a direction where function value is basically reducing. Okay, so function value is reducing. So in that case, what will happen, if f is a feasible direction, then this is basically, this term should be less than 0 and this term should be less than 0, because S is a feasible direction. Okay. I hope this is clear, because S is a feasible direction. So therefore this term st del g1 and st del g2 should be less than equal to 0. Okay. Now if suppose, so this we are getting. Now if lambda 1 and lambda 2 are equal, means is greater than 0, that means the lambda 1 and lambda 2 are is positive. Okay, lambda 2 and lambda 2 are positive, then what will happen? St del f will be positive, is not it? So if it is positive, this two term is positive, then st, because st del g1 is negative, st del g2 is negative. If lambda 1 and lambda 2 are positive, so in that case this term will be positive. So positive means, that means this indicates that s is a direction of increasing function value with respect to the your objective function. Okay, so with respect to the objective function, s is a direction of increasing function value. I hope this is clear. So s is a direction of increasing function value. So what does it mean? That whatever current point you have, basically, so if you go along direction s, it may be a feasible direction. Okay, it may be a feasible direction with respect to the constraint g1 and g2, but what will happen if you go along that direction? Then objective function value will increase. Okay, that is not a descent direction. Okay, so you are going towards the increasing function value. Thus we can conclude, that means if the lambda 1 lambda 2 are is greater than 0, okay, if lambda Lagrange multipliers are greater than 0, so we will not get any better solution than the current solution. Are you getting my point? So what I am telling here, so this is telling that if lambda 1 lambda 2 are 0, because s is a feasible direction, so if that is positive, so in that case what will happen? If you go along that direction, the objective function value will not decrease, it will increase. Therefore if you go along that direction, you will not get a better solution. So we can conclude that if lambda 1 and lambda 2 are greater than 0, then we will not get any better solution than the current solution. Okay, so therefore the condition is that lambda 1 at optimal point lambda 1 and lambda 2 should be greater than 0. Okay, so let us explain this, whatever we have discussed. So let us explain it here. Yeah, so we can explain. Suppose this is the objective function. So this the control, that red control line, so this is the objective function. So this is your capital Fx. Okay, and these two are constraints. So let me, so g1 and g2 are constraints. So on these constraints, that g1 equal to 0 and g1 and g2 equal to 0. Okay, so now this is the side, basically. So this is the side where that z1 z2 less than 0. That means if you go along that your direction, that your z1 z2 value will decrease. That means because g1 and g2 should be less than 0. Okay, so that is the constraint. So that is therefore, and this is the region where g1 and g2 are increasing. Okay, so therefore you cannot go along that direction. So if we apply the concept of feasibility here, so this is infeasible region, because in this case g1 and g2 will be greater than 0. So this is the infeasible region. So where is the feasible region? This is the feasible region. So this is the feasible region you are getting. So either this side or that side, so you are getting the feasible region, but on the other side you are getting infeasible region. I hope this is clear. That this is infeasible region, this is infeasible region, but if you are somewhere here, then the region is feasible. Now suppose you are at this particular point. Okay, so this is an active constraint. So as we have said, that this is an active constraint. So now this is del g1. So del g1 is basically direction. In that direction, if you go, the function value, that means the function value will increase. Okay, so therefore this del g value will means function value will increase along this direction. So now if you are taking a direction somewhere here, okay, so this is the direction, and this direction is feasible direction, because if you go along that direction you are in the feasible region. So I can say that is a feasible direction. Feasible direction, again, what does it mean? That function value will decrease. Okay, so that constraint function value will decrease along that direction. So because you are on that particular constraint. So now what will happen? So again, so we have actually said that this is del st. So now we got already this equation that st del f equal to lambda 1 st del g1 plus lambda 2 st del g2. Okay, so we got this. Now s is a feasible direction, so if you are going along this feasible direction, then this value should be less than equal to, this value should be less than 0. Okay, so less than 0. Okay, so less than 0. So therefore if lambda 1 and lambda 2 are positive, both are positive, so this is 0, this is less than 0, this is less than 0, and then if lambda 1 and lambda 2 are positive, then what will happen? st del f is positive. So what does it mean? That means if you go along s direction, the direction s, so in that direction the function value will increase. But if you recall, what is our problem? Our problem was a minimization problem. So that means I would like to minimize the function. That means if you are at the whatever current point you have, if you are going along that direction, the direction is feasible, but in that direction objective function value will increase. So therefore therefore whatever current solution you have, that is the optimal solution. Okay, so and this indicates that s is a direction of increasing function value. Okay, so thus we can conclude that if lambda 1 and lambda 2 are greater than 0, we will not get any better solution than the current solution. Or otherwise I can say that at optimal point that lambda 1 and lambda 2 should be greater than 0. Again, you please remember that whatever we are discussing, this is for the minimization problem. So in case of minimization problem, because if you go along that direction, the function value will increase, not decrease basically. So therefore whatever current solution you have, that is the optimal solution. Or otherwise I can say that lambda 1 and lambda 2 should be greater than 0 at optimal point, or you can say that that is the criteria of optimality. Okay, so I hope this is clear to you, and in that case yeah, so I can write the so I can write the necessary condition to be satisfied at constraint minimum points x star. Okay, so necessary condition is that this is the condition. Okay, so the partial derivative with respect to the variable should be equal to 0, that is partial derivative of the Lagrange function, and lambda j should be is greater than. So if that optimal condition is that lambda j should be greater than 0 at optimal point. Okay, so and this is for the active constraint. Again please remember that we have already divided the constraint in two groups. One is active, one is inactive, because inactive constraint we are not considering because they are not influencing the solution of this particular problem, so they are not active, but we are only considering the active constraint. So for active constraint, the lambda j should be greater than 0. Okay, so these conditions are called Kuhn-Tucker condition, and that is the necessary condition to be satisfied at relative minima of fx. So this is basically the condition called Kuhn-Tucker condition, and this is the necessary condition. Again, this is not the sufficient condition, but this is a necessary condition of optimality for constraint optimization problem having inequality constraint. Okay, but again what we have done, this is for the active constraint. Please remember, this is for the active constraint. So these conditions are in general not the sufficient condition. As I said, this is not the sufficient condition. So these conditions are in general not sufficient to ensure a relative minima. Okay. However, in case of convex problem, so we have already discussed about the convexity, what is convex function, convex problem. So for the convex problem, these conditions are necessary and sufficient condition for minima. This is optima but minima. Okay. So this is for the convex problem. Now question is that suppose I have given you some constraint. Now it is very difficult to know which are actually active constraint, which are non-active constraint. So basically if the set of active constraints are not known basically, then Kuhn-Tucker condition can be stated like this. Okay, so this is the partial derivative of the Lagrange function with respect to x, I should be 0. Then this is lambda j, zj should be 0, then zj should be less than 0, and lambda j should be greater than 0. Okay, so lambda j should be greater than 0 if it is not known. So and so this is the Kuhn-Tucker condition for if the active constraints are not known basically. So I have to consider this condition. Okay. So similarly, if we have a equality constraint something like this, so we have the inequality constraint. Okay, so you have the inequality constraint, that is so the problem is minimization of fx, okay, subject to zx equal to 0. So this is less than your equal 0, and hx is greater than 0. Okay, so hkx is greater than equal to 0. So this is actually we have now inequality constraint and equality constraint. So in that case the Kuhn-Tucker conditions can be written like this. Okay, so you please note that this is not k, this is h. Okay, so this is h. So okay, hkx is equal to 0. Okay, so in that case I can write it. So now this lambda j is basically for the inequality constraint, and beta k, this is the Lagrange multiplier again for the equality constraint. So I am getting the Kuhn-Tucker condition something like that lambda j, zj equal to 0, zj is less than 0, hk is equal to 0. Okay, so hk that are equality constraint, and lambda j, okay, should be positive. Okay, so lambda j is positive. So that is basically the conditions for constraint optimization problem with equality and inequality constraints. Now let us solve a problem here. So I will solve a problem now using Kuhn-Tucker condition. So this is an example problem. Okay. Okay, so this is the problem. The problem is that minimize f(x), which is equal to x1 square plus twice x2 square plus thrice x3 square, then subject to z1x is equal to x1 minus twice x2 minus twice x3 less than 12, and z2x is equal to x1 plus twice x2 minus thrice x3 less than 8. Okay, so now if we apply the Kuhn-Tucker conditions, okay, Then what is the first condition? The first condition is that del f by del xi plus lambda 1 del z1 by del xi plus lambda 2. So we have two constraints here. So therefore this is del z2 by del xi is equal to 0. So if I do that, so what I will get? I will get twice x1 plus lambda 1 plus lambda 2 equal to 0, and I'm getting 4x2 minus lambda 1 plus twice lambda 2 equal to 0, and I'm getting 6 x3 minus twice lambda 1 minus thrice lambda 2 equal to 0. Okay, then what is second condition? That lambda j zj is equal to 0. So then what I'm getting here? So I'm getting, this is lambda 1, so I'm getting lambda 1 x1 minus x2 minus twice x3 minus 12 is equal to 0, and second is lambda 2 x1 plus twice x2 minus thrice x3 minus 8 equal to 0. Okay, now the third condition is that zj less than 0. So what I'm getting here, I'm getting that if I put it, that x1 minus x2 minus twice x3 minus 12 less than 0, and I'm getting x1 plus twice x2 minus thrice x3 minus 8 less than equal to 0. Okay, and the fourth condition is that lambda j is greater than equal to 0. So therefore what I'm getting here, that lambda 1 is greater than 0 and lambda 2 is greater than 0. Okay, so we have written the Lagrange condition. So basically we have to find out a solution who will satisfy all these conditions. Okay, so that is the idea of solving this problem. So now let me do the question, that number. So suppose this is 1, this is 2, this is 3, this is 4, this is 5, okay, and this is 6, this is 7, this is 8, and this is 9. Okay, now from equation number 4, so what is 4? The 4 is this one. Okay, so 4 is this one. So from this 4, so I'm getting two conditions, are either lambda is 0 or x1 minus x2 minus twice x3 minus 12 equal to 0. Okay, so I'm considering, so from this equation, either so lambda 1 equal to 0 or x1 minus x2 minus twice x3 minus 12 equal to 0. Okay, so let us consider case 1, case A or case 1, that lambda 1 is equal to 0. Okay, so then if I put lambda 1 equal to 0 in question number 1 2 3, sorry, equation number 1 2 3, so here I am putting lambda 1 equal to 0. Okay, then what I'm getting, so if I say from 1, then 2 and 3. Okay, so what I'm getting, that x1 is equal to minus lambda 2 by 2, x2 is minus lambda 2 by 2, and x3 is lambda 2 by 2. Okay, so I'm getting this solution. Now if I put this in equation 5, okay, so where is the equation 5? This is the equation 5. Okay, so if I put in equation 5, so I will be getting what I will be getting if I put in equation 5. So we have that lambda 2 square plus 8 lambda 2 equal to 0, and from here I will be getting that lambda 2 equal to 0 or minus 8. Okay, so minus 8 is not possible. Okay, so because as per the equation 8 and 9, the lambda should be equal to it should be greater than 0. So the possibility is, okay, so from your question from 9, that if we apply from 9, so lambda 2 should be greater than 0. So therefore what I am getting, the lambda 2 will be, only possible value is lambda 2 will be 0. Okay, so if you're putting lambda 2 will be 0, then what is the x star? So x star is 0 0 0. Okay, so that is the solution. And if you're putting this in the other equation, so this will satisfy. So therefore this is one of the solution. Okay, so this is one of the this is one solution. Okay, this is one solution. Now let us do case 2. Okay, so what is case 2? Case 2 is that x1 minus x2 minus twice x3 minus 12 equal to 0. Okay, so now if we from suppose if we apply that question number 1 2 3. Okay, so 1 2 3, so I can write what is the value of x1 x2 and x3 in terms of lambda. Okay, so what is this x1? X1 is minus lambda 1 minus lambda 2 divided by 2. Okay, so from here I can find out the value of x1. Similarly, from here I can write the x2 value in terms of lambda, and similarly x3 also in terms of lambda I can write. Okay, so using equation 1 2 and 3, so what we have that this is minus lambda 1 minus lambda 2 by 2 minus this is lambda 1 minus twice lambda 2 by 4, and this is negative of twice lambda 1 plus thrice lambda 2 by 3 minus 12 is equal to 0. Okay, so if I simplify it, so I will be getting that 17 lambda 1 plus 12 lambda 2 is equal to minus 144. Okay, so I'm getting this equation. Now if you look at this equation, that lambda 1 and lambda 2 cannot be positive. Okay, so lambda 1 and lambda 2. So if you look at this equation, so this lambda 1 and lambda 2 will be less than lambda 2 will be less than 0. So that will actually not satisfy the our constraint 8 and 9. Okay, so therefore we will not get any feasible solution from this condition. So that means it is not possible. So it is not from this, it is not possible to get the positive lambda 1 and lambda 2 values. Okay, so that means from case 2, so we are not getting any solution. Hence, okay, hence the solution is that x star is 0 0 and 0. Okay, so this is the solution. And so, okay, so this will satisfy all the constraint. I hope this is clear to you. So okay, so I want that you please solve this problem, and let me know if there is any confusion to you. Yeah, thank you.